On an electroacoustic production line, faster testing means higher throughput. This makes it desirable to use a short test suite. However, longer averaging time improves noise rejection, leading to more accurate measurements. So how do you reach a good balance between speed and accuracy to get reliable results? If you are using a step sine sweep in SoundCheck, our harmonic track analysis algorithm includes tools to help you find the best combination of speed versus accuracy, like confidence limits, standard error, and noise. Confidence estimates the signal-to-noise ratio inside the step sine filter. The longer the averaging time, the narrower the filter, and hence the greater the measurement signal-to-noise ratio. I'm going to imagine I am testing a loudspeaker on a production line, and I want to get accurate results with the shortest sweep possible. Let's check all of these boxes and make a measurement so that we can see how it works. First, let's take a look at our step sine stimulus. Several settings affect its length. I'm sweeping from 20 kHz to 20 Hz using a step sine sweep with R40 resolution or 12th octave. At each step, I'm sweeping for a minimum of 3 cycles. The background noise, the signal-to-noise ratio, and the speed of the sweep all affect the measurement confidence. Let's run the sequence and take a look. We'll play this stimulus, acquire the data, and analyze it to get a frequency response. Using tools from harmonic track analysis, I can now look at the fundamental upper and lower confidence limits. These measurements are saved in the memory list, so if I put these on the same graph as my frequency response, I can see that both the upper and lower confidence limits diverge from the frequency response at high and low frequencies. We can also look at the total noise of the measurement. In this graph, if I use a different color, I can see that at the low end, the environmental noise is actually greater than the measurement, so our signal-to-noise ratio is leading to inaccurate results. So how can we improve this? We can try to improve the signal-to-noise by playing the sweep at a louder volume. I can make sure that I have enough input gain to have a good signal-to-noise ratio using the max FSD in to make sure we're at least minus 30 dB. I can also increase my stimulus cycles to reduce the influence of noise. Now, let's look at my stimulus step. I'm sweeping from 20 kHz to 20 Hz at R40 resolution, with each step lasting at least 3 cycles. SoundCheck allows you to define these independently. So now I have 121 steps from 20 Hz to 20 kHz, and each step lasts at least 3 cycles. I can also set a minimum duration for each step, and the sweep will satisfy both criteria. Increasing the number of cycles or the minimum duration lengthens each step, but improves noise rejection. If I increase the number of cycles to 20 and set a minimum duration of 20 milliseconds, it will satisfy either 20 cycles or 20 milliseconds, whichever is longer. At 1000 Hz, 20 cycles equals 20 milliseconds, so for anything lower, 20 cycles is longer than 20 milliseconds, and for anything higher, 20 milliseconds is greater than 20 cycles. So for example, at 20 kHz, 20 cycles is a very short amount of time, so the minimum duration will increase the amount of cycles to last at least 20 milliseconds. Now you can see our original sweep is 2.7 seconds, but let's update it, and now you can see it takes 18 seconds, which might be too long for a production line. To keep it shorter, we can make other changes, like change the step resolution of the steps from R40 to R10, so the frequency range is the same, but now we just have less steps per octave. If we update, we can see it shortens to 5 seconds. We can also adjust the frequency range based on what we really need to test our device. If we don't really need to test down to 20 Hz or up to 20 kHz, we could reduce the range to say 100 Hz to 10 kHz. Now you can see this brings the sweep length down to 1 second, which is much more appropriate for a production line test. Let's run the sequence again, and we can see what our measurement confidence looks like with these new settings. We can see now the confidence is almost exactly where the frequency response is. It's diverging a little bit in the low frequencies due to high total noise, and because the speaker's rolling off a little near 100 Hz. Let's try one more tweak. If we tried 10 cycles instead of 20, now the sweep is only 680 milliseconds long. If we run it, we can see that the confidence is much less, so maybe we do need to increase the cycles and go with a slightly longer stimulus. We can continue to optimize our stimulus step using these tools to achieve the best combination for our speed and accuracy requirements. And one last thing, if your measurement confidence is low due to noise, don't forget to try to reduce your background noise. This will probably have the biggest effect on your measurement confidence.